Okay, let's begin. In the last lecture, for those who like a small recap, we presented some, we tried to investigate what this clip-based model, so CLIP stands for Contrastive Language Image Pre-training, are actually learning and how can they generalize across different tasks and how robust they are in different datasets with different challenging datasets like cartoons and sketches. And then we switched to supervised learning. So the last part of the literature, this will be like mostly again centered in vision, will be to investigate the learner representation of self-supervised approaches throughout the different years. And then next week we will move to biological-based datasets like proteins and in general biological sequences for those who are interested in this kind of stuff and representation learning on those data. So one small thing that I would like to emphasize, there is some recent evidence about the limitation of contrastive language image pre-training, so contrastive loss between different domains. So we presented all the good things about the robustness and the analysis. However, recent research is able to illustrate some limitation of those models regarding how much they understand the text description. So they did some very small experiments playing with the text inside the sequence, like switching the position of the adjective and the noun, for example. Or in this example, instead of the horse is eating the grass, they switch the text description to the grass is eating the horse. And the model is not able to distinguish between these two and makes a lot of errors regarding this aspect. And the reason is that this contrastive pre-training, this contrastive loss, is kind of optimized more about retrieving images as a downstream task, and it doesn't need to understand the composition of languages that composes the text, so the sentence. Because if you remember, it aggregates the whole, it takes the CLS token of the text encoder, the transformer, which is kind of an aggregated version of those tokens in the sequence. So a global representation for the whole text description, for the whole sentence. And last time I also presented, I think it was 2 weeks ago, so they had this type of baseline. So this was CLIP, and if I remember correctly, different points in the plot indicated different architectures and different, let's say, iterations per training. So here, let's say samples C, and here, let's say, zero-shot performance on ImageNet on the image validation set, and this was CLIP, and this was the baseline about the image captioning baseline. So they had a baseline, as I said, with ResNets regarding image captioning, and they showed this efficiency. Okay, this is a straight line. They show that these CLIP models are much more sample efficient, but the recent evidence shows that this is not actually true. So the reason that these numbers were correct, what they presented, it was because these baselines were based on ResNets, smaller training schedules, and other architectural designs, rather than the objective of image captioning. So image captioning, for those who don't maybe want to refresh, it's like instead of having the label, this is like pairs data. So this would be image classification, and image captioning is the task where you try to predict a text description for each image. For example, in this case we can have the horses eating the grass. So recent evidence shows that you can get compared results regarding sample efficiency with pre-training based on image captioning, and in cases where the downstream task requires this, as we say, compositionality of language, to try to understand the order of the words, it even shows greater like downstream capabilities than clip, like contrastive based pre-training. But today, as we said, we move on the visual self-supervised learning to close with all the different pre-trainings where you can learn representations. This was just a small parenthesis. So let's start from the beginning. We have to consider between some self-supervised versus supervised transfer learning. So transfer learning, more or less representation learning. So I just want to emphasize, based on different studies from 2021, when should we consider supervised learning as a good candidate for our problem and our task? Does anybody want to make a guess? Okay. To answer this, we will always think of the pre-training distribution and the, let's say, downstream training data or task. So the answer is that first, the domain shift between the pre-trained in supervised learning, then we will switch to self-supervised learning. So the first, based on multiple experimental results we will present, is that you always need to consider how far away are these two distributions. So if you have like a very similar distribution, you have like a lot of reasons to consider supervised transfer learning. So for example, ImageNet pre-training, and then CIFAR or STL as the downstream, let's say, training data distribution. And the other reason that this, the other incentive that you might need to consider supervised transfer learning is that when you have very limited data samples for your downstream task. So then they showed that in this study from 2021 that this is like still a good, some good, let's say, like it's still nice to consider supervised transfer learning, and we'll present some results. So the second question is how these self-supervised, okay, they considered only convolutional neural networks with the abbreviation of CNNs. How do these pre-trained data, how they perform, not just on image classification on ImageNet itself, but on different downstream tasks. So we want to try to, so let's say the pre-training distribution is ImageNet, so we fix the pre-training distribution, and we change the downstream task, the downstream data, and the task. So we want to see how these features, as we say, transfer not just to different distribution, but also different tasks. Because we, in vision, when we say computer vision, we are not interested just to classify images and dogs. We are interested in many applications. For example, the most common ones are retrieval, object detection, semantic segmentation, and we'll try to provide some intuition for different downstream tasks regarding this manner. So the general trend holds. So for image classification, it's the ImageNet. So the performance on ImageNet really gives you a very good indication of how the model will perform by classifying other ImageNet natural images. However, when you switch to more to different tasks, especially the ones that require localization, as we say, for example, object detection. I have this image. So for example, if we want to say that the object, we want to draw like a bounding box inside the image, so we require some sort of understanding or localization of where the object lies in the image. So object detection would look like this in practice. You have an image, and you have 4 coordinates. So usually these 2 points. So you have x1, x1, x2, 1, 2. So this would be the target if you're planning to work on this kind of tasks. So these 2 points, 1 and 2, indicate these 2 coordinates here. So one can draw a bounding box. And there seems to be a relatively low correlation on how these learned self-supervised features, at least the ones that they considered in this study, because it's from 2021, so it was published in the beginning of 2021, so most of the baselines are from 2020. They found that there is a low correlation both for object detection and also for semantic segmentation. Does anybody know, maybe from the deep learning class, what is the task of semantic segmentation? Does anybody want to share it with us? Yes?
I think it's when every pixel has its own label, basically.
Yes. So you have a segmentation map. Usually, it's also called dense predictions. So for each pixel, you have like a label. So a discrete label from a set of classes. Let's say 10 different classes. This could be depending on the task. So for this type of data, so these are training data distributions and tasks, there is a low correlation. Okay, and the last question, which is still an open question, it's just that there is a reason that they didn't find like a clear winner between self-supervised methods. So the answer is that there is no like one general representation, even on the scale of those considered datasets. Even though the latest papers we presented the previous weeks, this Dino V2 version, for example, that is pre-trained on a lot of data with 2 objectives based on both this cross-entropy of different views and also for this masked image modeling objective, seems to be like quite universal for different tasks. So the last question is, okay, we have some images. So we have a set of images here. Image 1, image n, so we have a model and a second model and a third model. So we have different models. So in this case, we want to compare self-supervised and supervised models. And we want to know, okay, here we get some representations or embeddings for those images. But how are those? What are the features? How does these features compare to the one that we learn from supervised learning or from natural language supervision? So this is still an open area of research, and it's very hard to quantify how these features differ. That's why we need to define some downstream tasks and say maybe these features work better. So it's clear, like they have all the existing evidence shows that they learn complementary information, even though it's not like hardly established. And in this specific study, they also do some analysis based only on ResNets, and they say that the self-supervised features are not just more transferable, they are also more calibrated. This uncertainty calibration, so the model is not so overconfident as in the case of supervised pre-training. So they also argue with some small experiments that these features tend to discard some information related to the color statistic of those images. Can anybody imagine why the self-supervised features might discard these color statistics compared to supervised learning, who doesn't have this incentive to discard this information? Okay, I will give you the answer. The answer probably lies on the augmentations, because we distort the color statistics and then we maximize the information. So the model learns to ignore this part of the information. Yeah?
You can also do augmentations in supervised learning.
Yes, but not as strong. And the objective is not to maximize the similarity between those images and the features. It's just maybe you distort the statistics of the image itself, but in the end you want to classify the image. So you are incentivized to learn features, sufficient features so as to classify the image. For example, let's say a convolutional, one of the 1000 convolutional filters kind of understands this, some, let's say, face-based features, and this is more than enough to classify the image. So I just want to give you like a very rough idea about the complementarity of those learned features. In any case, they did some small analysis. So they, instead of using the features for a downstream task, they use those features and they train another model to reproduce the image, to reconstruct basically the image based on the features. Nowadays we have more recent baselines like these generative networks, like diffusion models, to do that, and they have much better results. But even with all their reconstruction based methods to reconstruct from the compressed version of the image, which is the features, to reconstruct the initial image. And they present this bar plot where the green one is the score of the supervised model. So mean square error means the lower the better. And the blue boxes correspond to the predictions of different self-supervised models. And they show that for the three different channels, the supervised model can reconstruct the images much better given this framework, even though it's not the most recent and optimized one. So this is the results, the main results they present. So the top part is classification on different downstream datasets. This one that's called DEX, it's semantic segmentation, it's pixel-wise prediction, and this is object detection. And in both of these tasks, you fine-tune the whole network. This is also important, and we'll emphasize on this. So even though it's like a really nice and large-scale analysis, the literature is not, there are not so many extensive and large-scale research regarding self-supervised, what self-supervised models learn compared to the illustrations that I presented last week from the clip-based models and the supervised models. So this result might change in a more recent study that considered vision transformers, and we'll see some similar results. So I just want to say that there is no clear winner between the transferability of the features in the scale of those studies, in this study, even in the same domain or in different domains. Okay, when you switch to an out of domain, or as we say, like a shifted domain, even the existing ResNets were known to have like not as very good, not as very generalizable features to Unseen distribution. Already with self-supervised learning, you can get better results in supervised learning. This is the general intuition. So out of domain and even a few shot, you have improved more relative and informative representations on your features with self-supervised learning. Okay, now we switch to vision transformers, and we want to investigate not just self-supervised learning itself, but self-supervised vision transformers. So, but by asking what they learn on their own, it means what are vision transformer learning with self-supervised learning. So the first study was just applying this contrastive learning pre-training with this momentum encoder, this exponential moving average. And they found out that smaller path size tends to help a lot on self-supervised vision transformers. Does anybody remember the overhead by reducing the path size on a vision transformer? So we have an image, as always, and then we have to decide what are these paths that we will project as features that will be the tokens, so the elements of the sequence. We design basically how many we will have based on the path size. So we take these non-overlapping patches of 14 by 14 or 16 by 16 or 8 by 8, and the more we reduce the path size as they write, the more we increase the tokens, the elements of the sequence in a vision transformer, which will hugely impact the complexity, because we discussed that the computational complexity is dependent on the square of the elements of the sequence. So with n elements, you have n square complexity in the self-attention layer. So when you reduce the path size, so n is height times width times path size squared. So you can see the impact by reducing the path size of the computational complexity of the model. So roughly reducing the path size, like using half of the path size, will give you at least 4 times more memory. So you can imagine it's very hard to implement this stuff. And another observation is that they can match and sometimes outperform ResNets, because this was the first study. And the last one was that the positional embeddings, so when we have the sequence, these are the tokens, basically are the path projection in vision transformers. We usually add another representation to be learned, which is a positional encodings or embeddings. Embeddings is that they are trainable and the model will have to learn. And it has been shown that they are not as informative as in natural languages, as important. All right. And another thing, and here I've highlighted with red the increasing performance by simply reducing the path size. So even though you still keep the number of parameters the same, so you see ViT large has 304 million parameters. By just reducing the path size, the performance goes up by roughly 3.5%. Whatever. So that's why I emphasize that I repeat and repeat all the time that the number of parameters by itself is not an indication of the complexity of the model, and you always need to take into account the complexity. You need to, like, the operations that are carried out by the model. And does anybody remember which metric I propose you to use if you have, like, in your own applications, how to measure the complexity? So given that you have a GPU with a specific memory, maximum RAM memory, the GPU memory you can say CPU, but they call it VRAM sometimes, you have to pick a batch size, a fixed batch size, that even your most large and most complex model can have the same batch size. So you fix the batch size, for example, to something that fits your memory, so 256. And you do inference for the whole validation set for different models, and then you calculate how many images per second you can process with this model during inference. So this is the most reliable way. So given a hardware and a maximum memory and the batch size, you perform inference on a single GPU with the model, and you see how many images you can process. They also show some better generalization to other datasets. I have them here compared to supervised learning, even with the first application of vision transformers. But we have already seen this kind of behavior. So the next model we will emphasize, which was the one that showed really remarkable results on vision, is this Dino with combined vision transformers similar to Moho. But they also showed that these models are not, the information on those learned features is, as we say, readily available, which means that you don't need to train a linear layer on top for each specific task. And this is very helpful in domains where it's very hard to get supervised data for the downstream task, because even with linear probing you need to have all the time something. But then these features are kind of, because this pre-training task of cross entropy is something like a clustering based approach, where you have to assign the teacher and the student need to have like the same class distribution in these over clusters, which are like at least one scale higher than the original data. And this seems to lead, combined with vision transformers, seems to lead to very good k-nearest neighborhood classifiers. So the features are already well clustered in the feature space, and by just looking at the 20 nearest neighbors you can infer the class. And here you can see that this is reflected in the divergence. So these models that perform similarly when you do probing, train a linear layer, they have a huge difference when you take the k-nearest neighbors. And you can also see, so from ViT base 16, you go back to a path size of 8, so this slash indicates the path size, and you see that the images per second drop from 312 to 63. So you can you need 5 times effectively more compute or more time, depends on how you want to quantify it. And this is the most reliable metric, so it's much better than the number of parameters by itself. And you get from 78 to 80, so more or less 2% performance gain. And this is a very nice illustration where at each epoch, so each, let's say, image on this moving GIF presents like a couple of ImageNet classes but the model is never trained with supervision. So the model learns this during training on its own based on the design augmentations. And you can see, I think it goes from 0 to 300 epochs. And these are some ImageNet classes. So it kind of learns a very organized feature space of the clusters because of this objective that we discussed, of this cross entropy that it has to assign the classes and the correct augmentations. And it seems to be able to connect classes based on the visual characteristics. There is some limitation to that. For example, in the lab we tried to cluster these features, and the model was not able to distinguish, because the visual characteristics are not all the time. You cannot, just from the visual signal, it's very hard to infer the label. You can think the example of what was the example of an analog telephone from the 80s compared to a telephone, like a more recent telephone. So it's impossible for the model to group these images together, even though the human annotates them as like mobile class or telephone class. So there is a limit to the features you can learn and distinguish with augmentations just from the visual signal. However, it's true based on visualization and k-nearest neighbors and all these benchmarks that these features are organized in a very interpretable way, even during training without any label information. So then we will switch to medical imaging, because I wanted to present again how these features transfer in different domains. So medical imaging is a very important domain of interest with a lot of applications for self-supervised learning, because the annotation costs are much higher and impossible to compete with the scale of annotations of natural images. So the largest proprietary data set from Google AI has right now around 4 billion images, and you can imagine that in the scale of medical imaging it's impossible to reach this scale. So self-supervised learning could provide like a remedy to those domains. I want to see if the features from natural images can be used on this domain. So this is some small motivation. And in medical images there are many assumptions from natural images that are violated. So for example, we don't have this idea of objects being centered on the image, and the structure differs significantly from natural images. And there are also cases where the images may not have the structure. So what do we mean by structure? So for example, there are some skin diseases from skin-based natural images, but we still call them medical images. And it's not that we are trying to look at a specific object. On the left you can see the X-rays, where the human expert would localize the disease. For example, this disease is called cardiomegaly, where the heart, usually on the left side, it tends to be larger. But it's not always the case that the images have maintained the structure of natural images. So these are 3 questions that one needs to ask when you work on a different application, like medical imaging. So how this model compare for medical downstream tasks. And the second question is that is it beneficial to take models from natural language, or is it better to train based on the specific domain, so let's say X-rays? Is it better to train a self-supervised model based on the X-rays that we have available? Or is it better to take the pre-trained model from natural images and transfer? And there is a lot of evidence pointing to the fact that it tends to be better if you have sufficiently enough data to train your own self-supervised model on your specific domain, like experts or X-rays or medical images. And this model tends to be better at learning features that are specific for your domain, even though they are not as transferable. You don't really care about the transferability because you care about solving the problem on your own domain. And the third, and maybe the most important thing, is that what do you do with the augmentation? So this pipeline that we have about color jittering and hue and saturation and cropping is designed for natural images. For example, you remember that we take some crops starting from 7 or 8% of the image. And if we have a medical image like an X-ray, maybe we lose the pathology in this X-ray by taking like such a small crop. So you always need to, the intuition here is that you always need to think about which transformations might be beneficial for your domain. And I will give some examples. So again, in this study from 2021 or 2022, they show that compared to, they took multiple supervised and self-supervised image models, so only ResNet 50, but different pre-trained self-supervised learned models and supervised models trained on ImageNet, and they see that they transfer much better the self-supervised learned features, even from the ResNet, transfer much better in a big plethora of medical imaging tasks. So I guess the result would be, the gap would be even higher if you use the recent vision transformers. And then this is the result about training your own data. So this is the result from a master student who worked with us in the lab. So given a large set of X-rays, like we have, there is a public data set with around 2,300 X-rays, and we try to see both in terms of classification and out of distribution detection. So here you can see, for example, how one would design which classes would belong to in distribution and out distribution. And we saw that by training your own self-supervised model, here, highlighted with the red, you can learn a much better, you can, both in terms of anomaly detection and in terms of testing validation accuracy. So the in-domain pre-training tends to be a very promising alternative in different domains, provided that you have the resources and the data to train your own models. This is some other results from my collaboration with some partners in the industry, where we use some cell painting data. I will present some pictures later. And we also used, I don't remember the exact scale, but I think like around 500,000 medical images of size of 1,000 by 1,000, and the images represent some cells based with different, let's say, drugs or perturbation applied on them. So we applied all the state-of-the-art self-supervised methods like Dino, muscle encoder, SimCLR that we have seen in the lecture. And we also saw that it's better than supervised transfer learning. So this blue is the baseline from supervised transfer learning. So I just want to emphasize that based on the projects that you may work in the future, you should always consider these design choices, for example, training your own models or your own domain and learning features for this specific application and downstream tasks. Okay, let's see some more design choices. Okay, for self-supervised learning, the main thing you need to take care are the augmentations. For example, in X-rays, there is this paper from 2021 that says that even though in natural images we use blurring, here we may be able to not be able to distinguish between the foreground or the background, or in general lose, as they write it, texture variations that might be important to learn some features regarding X-rays. So even though they didn't study, they didn't take this extensive ablation analysis by applying 2 transformations at a time, they try to adjust some parts, and from our results we saw that even if you take like fixed crops of, for example, 224 instead of random resized crops, it didn't have any impact on the learned representations. On our specific type of images, we use this cell-painting data, and we studied this in a similar way as in the paper from SIMCLR that we presented, the contrastive loss. So even though we saw that blurring helps in this application, we saw that the cell size, which is affected when you take random crops, we still want to allow the model to see variable sizes of cells, because that might reflect some actual, let's say, responses or changes that we might want to track. So in general, overall, all to all, you always need to think about the augmentations for each domain you're going to work. Okay, this would be like a more relaxing part and more interesting for many of you probably. We'll just take a look at some visualization based on different self-supervised models. So these are, even though I have presented the paper with Dino, I haven't presented a lot of illustrations. So this is for a patch size of 8. So it's pixelized, is the a visualization from the attention maps, and they have this they project it back to the initial image size with some sort of code they have, and they show that the different colors that correspond to different heads kind of learn this sort like this foreground background idea. So they try to learn, they actually learn some class specific features. So even though these images are a bit cherry picked, and as I will show later, this is not like as amazing as it looks in those images, the model indeed learns this foreground mask, this kind of unsupervised, I would say, segmentation mask. So instead of having an expert annotating each pixel, we already get, just from self-supervised pre-training, we already get from the attention maps this kind of visualization, which can be regarded both as a way to interpret what the model is actually seeing to make a decision, but also as some sort of unsupervised segmentation mask that one might want to use for some reason, based on the task or the problem you want to work with. And it's really intriguing that this property, this behavior, is not emerging as much with supervised learning. So even in supervised learning, where you train with cross-entropy with the actual labels to classify the image itself, you don't get this desired behavior, at least from the results that they present. So these 3 columns indicate the supervised attention maps compared to the ones that learned from Dino. And you also don't get this, let's say, cheap visualization with convolutional neural networks. There is a specific area of research regarding creating some sort of visualizations to this kind of interpreting the features of the components, which we will not cover in the course. I'm just saying we need both vision transformer and this type of self-supervised pre-training to get this behavior. And there is another work, kind of a concurrent work, that showed that you can also train a vision transformer instead of just supervised, also with this distillation-based features. So some features from a resonance that is trained on this specific data set that it's kind of stylized ImageNet. I presented some pictures last time where they modify the renderings and stuff so that the model is impossible to classify the image just from the texture, and it needs to learn this shape. So they had some sort of similar maps, but it mostly emerges with vision transformers and self-supervised learning. And it also works across domains. So this is from some blog post online where they applied this dyno approach with the vision transformer trained from scratch on histopathology images. So this one is GT, corresponds to the ground truth, so the human annotated label, and these three colors, 1, 2, 3, correspond to different tissues in those images. For example, one may correspond to, let's say, fat tissue. And these are the 6 attention maps from the 6 heads of the last layer of the transformer. So I think it's quite convincing that the model learns informative features, even though it's still qualitative. There is no quantification. And these are from our models on these cell painting images. So these are the 5 input channels from those images. So this is a specific image technique to get this type of microscopic images, this type of medical